So Paul, where did you come from? Are you nearby, Tim?
For the last 2 weeks, I've been in London.
Oh yeah, tell Keith the story. So they raised some seed capital about 18 months ago, and then they set a date in February, did you say?
Yeah, so what the deal is, I think sometime in 2022, George and then his co-founder Taylor, they were, George quit Tesla because he thought that the way that they were proposing to fix autopilot, in particular to fix the quote-unquote San Francisco problem for autopilot, was just way more data for San Francisco specifically, and just throwing compute at the wall. And so it was like this. So George's thought was like, this can't be the right way to do it. So he was like, I'm not exactly sure how to do this, but I want to take a bet. I want to take a position against scale.
It kind of feels like they're trying to memorize infinity.
That's correct.
So, would you say that your experience there informed some of this skepticism?
Yeah, I mean, I think if you look at the AI Day presentations that effectively go into deep technical detail about how Tesla learns the world, or Andre's talk at NeurIPS 2 years ago, Tesla very much is trying to come up with a function that memorizes the world. Basically take all of the possible perceptual states that exist in the realm of driving and produce the correct perceptual signals that result from that under all circumstances. And they're pouring massive amounts of training data into making that happen, running tests in shadow mode to collect triggers that then feed more labels back to the labeling team to run that data loop. Operation Vacation, which has been publicly discussed, is effectively that singularity moment where the function converges and has memorized infinity. As I've kind of talked to you about so far, I do not believe that that's possible. Obviously neural networks are finite machines. They operate under finite compute constraints with finite memory. It may be possible to build a neural network that could indeed memorize infinity given an infinite number of layers, an infinite number of fully connected neurons. Infinite compute and memory to execute that model. But given the compute constraints in a Tesla vehicle, I don't think that's possible to achieve.
And so then he shopped around for a year or so to try and find a venture capitalist to fund a sort of research-oriented venture to, make a case for you can do a lot of things without scale. And then I came on to the company about 6 months ago, and within about a month and a half, we were like, okay, we don't know what we'll be doing in 6 months, but we need to be selling it to the investors in 6 months. And so we finished the paper on February 1st, or really February 2nd for the North American time zone, because it's, a February 1st anywhere on Earth kind of thing. And then a week and a half later, we were meeting with the venture capitalists to get money to do this whole thing.
Yeah, quite a whirlwind. I mean,
yes,
I'm just thankful that George created this and it exists, because I think I take the same line conceptually, which is the answer isn't just more of the same.
Yeah,
more of the same. We need to go back to some cleverness and invent some new things and to really make order of magnitude improvements.
Doggo, you should see this setup. We've got you on a big 55-inch plasma screen, so it's as if you're in the room with us.
I'm sorry about that.
That's too much, Doggo, is what you're saying.
I would have shaved or brushed my hair or something.
Well, I mean, you did pat it down in the back.
The headset, yeah, it's like this headset hair you get,
wearing
a headset. So I'm actually getting worried about that. Like, what's the compression gonna do to my ear cartilage over time? All these unknown cybernetic effects.
A very soft version of cauliflower ear for podcasters.
Right. I guess something you could be proud of, right? Just like the MMA guys are proud of the cauliflower ear.
I've had this headset on for so many hours.
10,000 hours of Skyrim alone.
I have achieved true mastery.
Yes.
Okay, well, we're in.
We are.
We're in. So Where do we start? I mean maybe Paul, because Keith hasn't watched the recording of the other day, so maybe if you just frame up what's going on here, and in particular, I think we want to have the Turing machine discussion with you with Keith on the call. So yeah, I mean just frame up the what's this all about?
Okay, what the hell is this all about? Depends on which side of the collaboration that results in the paper you are on. If you come from the DeepMind side on this, you are looking for a generalization, of geometric deep learning, right? There are some obvious limitations to geometric deep learning, which is that the kind of transformations with which you can, or relative to which you can ask for a neural network to be equivariant, are invertible and always composable. And so on their side, they're thinking, okay, we need to generalize away from invertibility first and then generalize away from the presumption that all transformations can be composed, right? Because not all computations can be composed. So if you want to use something like GDL to align neural network architecture to algorithmic challenges, you need to figure out a way such that you can align it to these not necessarily invertible, not necessarily composable steps of computation, right? If you come from it from where I come from it, it is, I'm interested in neural networks as a particular instance of morphisms in a two category of objects, parametric maps, and reparameterizations, and I'm interested in the kind of structure that they're interested in, but thinking about it as, algebras for monads or co-algebras for comonads, stuff like this, right? So this sort of I'm not going to say like higher level of abstraction, but much more sort of two categorical flavor, whereas they're really thinking in terms of sort of representation theory and a sort of generalized version of representation theory. Bruno and I, Bruno first, right? I learned what I know about neural networks through reading Bruno's thesis, and that collaboration's been really instructive. But we've really been thinking about this as, okay, there's a two categorical story here. We want to do two categorical universal algebra. And this gets you way more abstract, which makes it more fun to think about, but it also makes a lot of things tractable that are otherwise far too complicated to reason about.
I think just as a very tiny kind of question, I think it'd be good. I think most of our listeners can definitely understand that some computations are not invertible.
Yeah.
That's easy. I mean, you add two numbers together. It's like you don't know what the original two numbers are. They
right.
could be a bunch of possibilities. It's not invertible. But can you give us an example and some intuition behind computations that are not composable?
Oh yeah. So this is sort of like what, in some sense, this is what type is for, right? Consider some like a computation that requires that the input be a tree cannot be, at least not naively, applied to something that is lists. Right, you need to do a conversion between lists and trees before you can apply a computation that takes in trees to it. Right, so that would be an example of a non-composable computations. Right, stuff where there's like, well, the types of the input and output simply don't line up.
And isn't another example, and correct me if I'm wrong, but I think another example is something like branching is not, at least unless you're in a non-deterministic paradigm, like branching is not composable, right? Like if I have an if statement that kind of says, if it's one thing, do this, if it's something else, do that, then that poses some issues for composition, for function composition, right?
I wouldn't say that. The reason I wouldn't say that is because the function if this do this, right? I can still compose stuff afterwards. It depends on if my if this has a different type, say, than if this do that. Then you might not be able to compose like stuff together naively. But I wouldn't say that conditionals and branching are really what the issue is. It really has to do with input and output types.
Right. Well, I think the concern there, it is a type one kind of, at least from, and let me first state up front, I'm super interested in category theory. I know very little about it. I only have, I've tried to do some tutorials online, and so a lot of my knowledge is pretty far out of date. But I think like the issue with composability of branching, at least like say in the Haskell, kind of functional programming world, is that even if both of the results are of type T, the outcome of that branch is possibly a union of it's an optional or a maybe of those types. Like it may be one value or another value.
Yeah.
And so it kind of creates this. Is that right?
Well, I mean, but the thing is, like, maybe something is still just one type, right? So I really
right, but it's not T, but it's not type T.
Exactly. You have to.
It's a higher order type.
Yeah, yeah, it's another type, exactly. And so you can't simply plug maybe T into, like, you can't simply apply something that requires, takes input of type T to something whose output was maybe T, right? You need to do like, oh, I have to check is this just T or is this like, else or whatever. I can't remember what the Haskell syntax is, right, for the exception.
Right, and so that's the problem with branches is as soon as you throw in branches into code, you start to change the type into these, composite types.
Okay, so I'll in that sense, I will buy that. In that composition, you have to be much more careful about type. So I think it's still a story about input and output types and which things you can compose. But the problem is naive composition. If you start doing branching of things, you realize, oh, I've actually changed what type I'm dealing with.
Yeah, and so just back to my own personal story a second, because I have a question I'd like to ask you, which is. A long time ago, I learned about the power of algebra. So when I first took an abstract algebra course, I was like, wow, this is really cool. Algebra is so much more, right, than I thought it was. Then sometime later, I found out just the real beauty of type theory. And this is all within a computer science perspective.
Yeah.
So algebraic data type theory, types, I fell in love, right, with types.
Yeah.
Okay. And so then along comes somehow I hear about category theory, okay, and I'm like, oh yeah, this seems to be, if I go learn some about category theory, it's going to help me understand software better and, algebraic type theory and everything. But what I sort of quickly found, and again, this could be quite naive, and this is why I want to ask you, is that it seems to me like type theory is, it's this higher order thing where, for example, you might look for similarities between algebras, like, here's the algebra of Boolean algebra. Here's the algebra of partial orders. And they're actually maybe the same algebra, or they have a lot in common. And so there's this beautiful sort of high order pattern finding and relationships that allows you. You might be able to prove something in one algebra, and it gives you the tools to map it into a different algebra. But I found it didn't really have a lot of relevance to me just for my everyday software engineering. And so I started to kind of lose, the interest in it. Tell me where I'm going wrong. Tell me, in what ways category theory can help someone who's more of a practitioner, a computer scientist, a software engineer, really understand better what they're doing or apply new insights, to the kind of work that we would do.
So unfortunately, I am not the best person to answer that question, but I'll give it a good shot anyway, right? So I come to this whole story from pure mathematics, and I discover type systems in the context of homotopy type theory, where it's like, what? There's a programming language that corresponds to space? Okay, right. So my introduction to this stuff, I come to I actually way back in high school or whatever, I learned scheme and stuff like that. But that was longer ago than I would like to admit, and hadn't been terribly relevant to my intellectual life in recent years. But so I would say the problem with trying to justify category theory in terms of functional programming alone is that you've already learned most of the category theory that's going to be directly relevant by doing the functional programming itself. Right? The point is, you don't get Haskell without category theory. But once you learned Haskell, you've learned a lot about a specific category, and that's the only one in which you're actually doing all that much work. So the abstractions of category theory don't necessarily give you all that much. Right, that's sort of my naive perspective on it's category. I remember the first day I came into the Symbolica office when we were next door to Coastal Ventures, and I come in and one person's there, and they're like, "Oh, you're the new category theorist. I hear that's useless." And my retort is like, "You like functional programming, right?" And they're like, "Yeah," and I'm like, "That wouldn't exist in its current formulation without category theory. It's like, yeah, but I know it through all of these other means. It's like, yes, you've grokked the essence of the category theory that is applied to functional programming most of the time already. I do think that once you get into things like dependent types and sort of more sophisticated type systems, the category theory side, you need more sophistication to make really good sense of it. You can have sort of a pretty good elementary in the sense of like, I think about elements or I think about terms way of thinking about things like dependent type systems. But I found, of course, this is how I came to this stuff. So of course, I think this is like the right perspective, but I think that category theory gives you permission to have a sort of more geometric interpretation of this stuff that makes it easier to understand and easier to reason about, right? One thing is like the real strength of category theory is not like working in any particular category, right? The real strength of category theory is, hey, this gives me this principled language and theory for abstracting things such that I can remove all the extraneous detail from a particular problem and study just the bare bones of that thing, get an excellent description, an excellent understanding, and find it in lots of different places, right? So it's the idea, it's sort of, like, I want a good library. I do it once, and then I apply it in lots of different contexts.
And I'm absolutely not one of the category theory is useless people. I think I'm in the category of, I think there's probably a lot of really useful stuff in there. I just I definitely don't understand it, and or it hasn't been discovered yet, for my particular context. But let me give you an example where my intuition tells me there's probably some really useful insights from category theory to be explored. So long ago, Alexander Stepanov, a really brilliant, computer scientist, was trying to do things within type systems that were just not possible in the current languages. So one thing he wanted to be able to do, for example, was to have a type system rich enough that it could express properties of an algorithm. So maybe you have a bunch of different sort algorithms in your library, and he wanted the kind of complexity constraints of those sort algorithms to be part of the type system.
Yes.
So that somebody writing a generic piece of code, calling a sort algorithm, and there were certain properties required there, that the type system could make the best decision. Like it could say, well, in this particular case, you should use this sort algorithm. And it was able to compute all this like from the type system.
Yeah.
He eventually discovered C++, which just by accident, it had a template metaprogramming capability that wasn't by design. It just kind of accidentally ended up being a Turing complete, type system or whatever, where he was able to implement some of his ideas with really ugly code, by the way. So I'm not justifying, the quality of it. He just was able to, and he was able to do, lots of brilliant things, which led to like ideas like, traits and categories in their sense, like in the kind of, and, algorithms with very rich type systems, template metaprogramming. I feel like we've hacked our way to that, like by accident, kind of from the computer science side, from the programming side of things. And the category theory could offer a new lens to view that, and provide insights for designing like the next generation of languages and advanced type systems. Is there any sense to that, or I'm off the rails?
No, I think that's so. One of the things that like I'm not working on this kind of stuff right now, but I have spent a lot of time thinking about, and is essentially starting with a particular category and then trying to define a domain-specific language for that, or like an internal language of that, such that it becomes easy to reason about the stuff in that category in a way that's perhaps a little bit more intuitive than going towards like the high structuralism of purely category theoretic arguments. Right? An example.
So I love that. Let's pause there for 1 second. So I love this idea. So category theory can help one design domain-specific languages.
Yes, no, this has been like become a huge deal. Like I only know of it from like the homotopy type theory community and the kinds of projects that has spawned. But as an instance of this, so there's this paper I think by Mike Schulman called a called A Practical Type Theory for Symmetric Monoidal Categories. And what he does in this paper is say, okay, there are a bunch of type systems that are interpreted into symmetric monoidal categories, but no one uses them for proving things about symmetric monoidal categories. And he asks the question, why? And he essentially, nails down a couple of points that all of the existing type theories that are interpreted into symmetric monoidal categories fail to satisfy. And like the one that I found the most compelling is like they don't have this sets with elements flavor to them, right? And what's prerequisite for sets with elements and that feeling is, well, you need tuples of terms to be in tuples of types, and that needs to be symmetric on both sides of judgment. Right, and so he says, okay, I'm going to design a new type system that has that property with my intended semantics in symmetric monoidal categories. So the idea is you can design a programming language, so you can you can have like the semantics that you want this thing to have, and then design the programming language to fit that. Right, and I think this is an incredibly powerful. Powerful trick that I do believe it's taking longer than people thought it would, but that's okay, because it's hard. But the idea is, what you can select. Kuhn has this line about, the only reason science works is because you can forget how you got there and just start from new foundations each time, right? It's kind of like a less snarky analog of the, science proceeds in funerals kind of thing. It's
exactly,
like you don't want
you don't
to have to recapitulate all of mathematical history to work with something. And we're finding out that there's all of these like complicated mathematical structures that we really want to reason about, and we don't want to have to build them from scratch. Instead, we would like to start with something like a programming language or a logic that just deals with all the complexity of that naturally by forcing you to be careful about syntax.
Yeah.
Right. And this is the kind, and so this is exactly this whole study of like domain specific languages for categories, or better in mathier language, this is like internal language hypotheses or internal language statements. Like I want the internal language of this flavor of category, or the internal language of this flavor of category. And so maybe so this is, you can ask the questions like, why the hell are we getting to, why now, right? There's a good deal of why now, right? I've just said is like, hey, we've just had a successful funding round. We've got $31 million. We're assembling like the world's largest industrial category theory and machine learning team. The immediate response to this is like, aren't you the only category theory and machine learning team in the world? Is like, no, there's probably like a couple of them. There's like Pitar's team at DeepMind, that kind of stuff. So we're not the only people in the world doing this, but we'll probably over the next 6 months become the biggest. And the question is like, how the hell do you get money for this? And one of the reasons is, if you look in the history of computation, there have been people banging the drum of purely functional perspectives and category theory as the right foundations for computing, but you haven't needed it before, right? You've been able to hack your way with other paradigms, but deep learning and quantum both pose problems to the existing paradigms. It's just it suddenly becomes too hard to make progress without categorically informed treatments of those computational substrates.
Right. And so let me ask you about this, because I haven't read the paper yet, so apologies for that. But I think if I'm going to take a wild stab based on everything you said so far about where you might be going from this perspective, is it the case that category theory will inform the construction of domain-specific languages for machine learning?
That is definitely one outcome that I foresee.
Okay, and so in my kind of, let's say, more lay understanding of that, it would be say as a practitioner, I would now have a language that I could use to maybe even define modules, machine learning modules, or constructs, compositions of neural networks in a way that I can actually reason about as a human being, because there'll be a new set of concepts, a new language that I can program in, if you will, which will ensure the semantics and structure that I need to do something useful.
Yeah,
right?
That is exactly right. One of the outcomes of this research program, we hope, will be something we can call type-driven ML or type-driven deep learning.
Yeah, I mean, on that, we had a very interesting discussion just before we hit the record button. And, there's a real problem now with ML engineering, but also just large-scale ML systems like Facebook, and it's inscrutability. And this is a real problem, right? Because we tend to just blame the system, and it gives gainful employment to lots of engineers because we lie. We say that these things reason, that they operate in a rational way, and they don't. And when they go wrong, we just blame the system. We just, it's just a complicated neural network. That it's like alchemy, both in how we build the systems and how we explain the failure modes. And what you're talking about is a future towards not only having a formal way of understanding and verifying programs, but just being on a more solid footing for how we build systems.
Yeah, no, precisely. Our aim is very much to refound deep learning in such a way that you can actually do careful reasoning about it, right? That you can actually do theorem proving about the behavior of these neural systems, right? Whereas currently we're hacking everything together and we use benchmarks and heuristics and all of this stuff. Like, we can do better.
Yep.
Right? We know that we can do better with classical programming. So why can't we do better with neural networks? Lots of people say, oh, you simply can't do that. Maybe software engineering has to be like neuroscience. And I think it's like, well, there's definitely going to be something like that there. But a lot of it is formally structured, so that the key will be to evince that which is formally structured and pull as much out of that as we can and make that explicit so that we know the bounds over which this thing is doing some like inscrutable curve fitting, whereas in other places it's doing this very formal stuff.
So I mean, that point is really interesting, that people have said to me that they think the future of software engineering is like neuroscience. And what I mean by that is we don't know how the brain works. We stick probes in and we try and kind of figure out what's going on, a bit like the blind men and the elephant, by having all of these different views on this inscrutable mountain. And it's just a little bit weird, isn't it, right? So, we're building these multi-agent systems and they have all these complex dynamics, and we try to apply engineering techniques by doing monitoring and alerting and having these like weird thresholds and just fixing problems as they show up. And a lot of people just say, well, this is the way things are. This is the way software is going to go. And as I understand software engineering, because Keith and I have written a whole bunch of complex software recently, and part of the reason for having abstraction is to create a cognitive interface. So it's not necessarily about how the software runs, because it gets compiled into low-level code, native code on the machine. But it's about creating an abstraction to help us understand and communicate what's going on, and also do forms of verification later.
Yeah. No.
Well, and that abstraction is a domain-specific language, and so every programmer, when they're creating whatever, just a bunch of functions, a bunch of modules, a bunch of classes, whether you know it or not, you're designing a domain-specific language, and we kind of just do it intuitively without much sort of math helping us. And I think the point is, if I understand both of you correctly, machine learning and quantum computing, it's just beyond our capability to do that. Kind of just intuitively, we need math.
It's just too hard to hack it together anymore.
Right.
Yeah.
So I think that's beautiful. I mean, and I, in fact, there's a very old programming book from the 1970s. I think it's called Programming Languages, or Designing Programming Languages or something, which tries to make this point too. And it makes two interesting points. It says, when you're writing a program, whether or not you know it, you're creating a domain-specific language. And so knowing something about programming language design is helpful, even to just writing code. So you said there or at least one thing you hope comes out of this project, Paul, is machinery to create domain-specific languages for machine learning. What are the other things that you hope comes out of it?
The other things that I hope come out of it are completely novel architectures. Yeah, so completely novel architectures that can do kinds of things that we currently don't know how to do, right? So one thing that you might want to do is so I'm in industry now. I'm not an academic anymore, right? suddenly I have to figure out how to eventually generate revenue with this foundational research. Say, what's one of the, like, so consider Microsoft, for example, right? And this is, a story that we've been telling for some time, is consider Microsoft and all of the different places that they are deploying AI systems, or LLMs specifically, throughout their whole, panoply of offerings. The only one that's actually making any money is Copilot, right? But Copilot is not actually very good, right? LLMs are not actually very good at generating code, right? They'll like regurgitate some snippets, but like a staggering portion of the time they're wrong. The fact that we're used to this is because like when humans generate snippets of code, for a staggering proportion of time they're wrong. So we're not offended by this, right? But so if you could make something better, such that if you have an LLM that you can interact with in natural language, but that actually emulates a type system, right, you will end up with an LLM capable of doing higher order processing, higher order organization. You'll note that I'm intentionally shying away from using the word reasoning, because I sort of take exception to this language. I understand it to be the lingua franca of the practice, but I don't really like the language of reasoning, but I'll accept it.
We take exception to it as well.
Oh, we very much do. But can we just linger on this point? This is a fascinating point. Now, there are a lot of people out there drinking the Kool-Aid right now. So there was the Codex model, which is what is built into VS Code, and that's garbage. GPT-4 Turbo is pretty damn good. Anthropic Opus is pretty damn good. There's this thing called Devin, which came out recently, and people are saying, oh my God, there's no limit. We're going to start getting this thing to generate code, and then we're going to fine-tune the base model on the outputs of the code, and it's going to be a bit like evolution. It's just going to complexify, and we're going to memorize all of the types of reasoning and all of the types of things we're ever going to see. And I think that a lot of the people who are drinking the Kool-Aid about this just don't do serious software engineering. And that's because, like, for example, I was playing with Opus, Claude 3 last night. I got it to generate a man animation of a bunch of mathematical, graphics. Yeah. And it worked really well. I thought, bloody hell, it just worked first time. I then said, well, can you modify it a bit, and can you add this thing? Very quickly it diverged, and it turned into garbage, and it was useless. And that's because it's almost like we're wrestling on the boundary of chaos, right? So the complexity of software blows up so fast. It is possible to do something simple, but as soon as you modify it and you change it, you're in no man's land very, very quickly. And I think part of the reason of having this structured approach, this abstraction approach, is to wrestle with that complexity. So you're making the argument that if you're doing something like a large language model does now, but in the abstraction space rather than the low-level syntax space that we do now, then we can get further than we are now. That
is precisely the claim. There's I think it's a relatively recent paper by, I think the team was led by Talia Ringer, excuse me. I can't remember which university it's based out of, but it's a great paper, and it demonstrates pretty conclusively that transformers just don't learn recursion. Right.
Yeah, of course.
There you go.
And so, like, why would you ever think that by scaling an architecture that is likely to have fundamentally architecturally, like by construction, limits on the kinds of things it can even figure out?
Yeah.
Right.
Yep.
Why would you ask a system that can't do recursion, which we know to be the essence of programming, at least in some sense? Right. Why would you presume that model is ever going to be capable of doing the kind of software engineering that we actually need to do in the world?
I mean, I think it's almost even worse than that, because they can kind of mimic recursion to a fixed depth, because they have a fixed amount of computation, right? But even worse than that, the real problem is they can't create abstractions, because creating abstractions it's abduction.
Yeah, and I think they probably do create abstractions, right? They've got like latent representations, but the problem is like the abstractions are not good. They're not principled.
Oh, but I would argue that we create abstractions, and we embed them in our language, and then they get memorized by a language model, and they can be reused. But what we do when we design software, we solve this intractable problem. It's very mysterious how this happens. We select an abstraction from an infinite set, and then we use that to represent a concept. And language models do not do that.
No.
Yeah, I mean, on the recursion thing's really interesting, because we were having a conversation the other day about So there's this really exciting technology you're working on, and as we were just saying, it's a way of building a semantically principled way to design the future of neural network software. So you're rather than dealing with these inscrutable neural networks, we're actually dealing with compositional structure with clear semantics from a high level. But the problem is, as I understand it, the end result is still a neural network, and neural networks are finite state automatas, right? So they don't do recursion. And then there's this notion that came up, because we were talking about this over dinner, and there is such a thing as a recursive neural network, but a recursive neural network is still a finite state automata. The difference is we can modify backprop to recurse over a structured input. So for example, we can put trees into these things.
Yeah, so they can do structural recursion.
Exactly. So we can, because a recursive algorithm has a kind of stopping condition or a base case, if you like. So we could put a tree in, and then the algorithm can recurse that tree. And what it's doing every time is it's just embedding every single. You start with the leaf node, and then you go up and you go up until you get to the top, and it's just incrementally embedding that datum into the neural network. But the neural network itself, it's still doing a fixed amount of computation for that input.
Yeah.
So I guess the question is, what we're really excited about, PET has been working on this for years, is algorithmically aligning neural networks. And even GDL more broadly is about constraining neural networks so that they generalize better within distribution on geometric priors. Yeah. But the thing is, they still only generalize within distribution. So they don't act like Turing machines, which is to say they can't address an expandable memory, potential infinity. They can't just go to Costco and get some more memory when they need it. They do a fixed amount of computation per datum.
Well, so this is this particular question is outside of my domain of exact expertise. So I want to be careful about saying, anyone who's says, oh, this person said something wrong. It's yeah, I'm not claiming to be an expert in this particular domain, but this sounds like a story is they can do coalgebras, however, right? And coalgebras are things where, yeah, you can just keep popping something off, ad infinitum. You can just query it. Hey, give me this part of this, give me this part of this. And there's no stop to how many times I could ask for that, right? So I can do coalgebraic stuff too. But my sense is that maybe this is some sort of more definitional confusion than it is really a statement of the kinds of things that neural architectures can do.
Yes, I think I can probably help clarify it, because for better or worse, we've been having a lot of debates in our Discord, recently about this topic, and so I think maybe we'll test it out here today. I've learned how to communicate this, a little bit better, to try and explain the pragmatic, problems with it. And so if we think about, first of all, just to set up something very clearly, if we all understand what a finite state machine is, just imagine it as a graph, it sits there and it can get input. And by the way, it can get an unbounded amount of input. You could, for example, a soda machine.
Yeah, you can keep feeding it instructions as long as you want.
You can keep pressing the button and putting in quarters in it all day long, and stuff will continue to happen forever. The point is that it has a fixed number of states that are defined at build time when it was constructed, and it just navigates between these states, always kind of responding to the input. That's a finite state automata. A Turing machine is, and I say nothing more than, but by the way, guys, this was a genius, discovery, back in the day. A Turing machine can be boiled down to nothing more than a finite state machine that has an expandable read-write memory. Or another way to think about it is it can have two stacks. It can push a value onto one stack or another stack. It can pop a value off any one of those stacks and push it down. So it has this expandable read-write memory that's unbounded.
Yeah.
That machine alone, that simple machine alone, in fact, is powerful enough to perform all computations, all what are called effective computations. So any mechanical thing you can construct, any physical thing that you devise that has a digital nature and do stuff, is no more powerful than this machine. And that includes, by the way, quantum computing.
Yeah.
So quantum computers are still just Turing machines. They can do certain problems faster, but they can't fundamentally solve any problem that a Turing machine couldn't solve. Okay, so getting to neural networks. Like, it should be immediately obvious to anybody that a neural network has that finite state machine component. That's what the neural network is. And now you ask, can I hook that up to read-write memory, right? And have that neural network do something useful. The problem we run into is training the neural networks to do something useful with unbounded read-write memory. Like, we don't usually do that. So all recursive neural networks that are trained today, they have a fixed window ahead of time that's known at training time, where they do like operations on whatever, a context of 100,000, or they sit there and operate on 100 windows or something like that, and then you take the answer that you get at that point, like you've got an output signal. Whenever people try to train them to do unbounded calculations, like for example, maybe I'm going to have an RNN, and whenever one of my bits lights up in the output, then I'm going to treat that as halting, and I'm going to take the answer at that point. Okay, so I'm going to run the Turing machine during training. As soon as bit number 26 lights up, I'm going to treat that as the halting bit, and then I'm going to take the answer. That could be a Turing machine. The problem is when they try to train machines like that, we just can't do it. And so if you think about the space of all possible programs, like the space of all possible programs are the Turing machines, okay? And we're doing a certain search. So today we've got the capability to construct all kinds of neural networks and use stochastic gradient descent or whatever. We're searching that space of all possible programs, and we're finding one that does something useful. What we're finding is that space that it searches is a very small subspace of all possible programs, and it's really those that are also reachable by finite state automata. So we're not getting out of that boundary up into context-free grammars, context-sensitive grammars, recursively enumerable languages. So there's this huge other space that we just don't know how to effectively search efficiently with machine-driven techniques yet.
Yeah, I mean, I will confess I could be wrong, but I don't think that is, I think that's sort of an accident of particular definitions and the way that we've been structuring neural architectures, right? And what I mean by aspects of definitions is like, yeah, if you pretend that your thing is of like fixed depth, but if you allow feedback into the system, then suddenly you can get, I do think you could get access to that higher order computation.
Well, I think it's actually just an accident of our optimization procedures. It's an accident, not so much of like the architecture is fine. Like you said, people do have, RNNs that have feedback and all this sort of thing, but it's an accident of the way we train them. So when we go to train them, nobody currently trains in the way that I just said. We're like, when I do a training pass and I go to propagate my gradients, I never sit there and run the neural net, the RNN, until a particular bit lights up and then take the answer. I run it for a fixed number of steps and take the answer.
Yeah, well,
because the problem is if you try to run it until a bit lights up, it may never light up.
Well, no, you can guarantee. Okay. So I see the concern. Well, so what if you consider that? Yeah, I mean, I don't think this is a real problem. I think this is a question of misconceptions. Maybe some that I have, or maybe some that are popular in the ML community, to which I'm like a quasi-expert in like CT world, and like I'm learning, using CT to speed up my process of developing expertise in ML. But I don't think that this is a permanent problem, like in the sense of like that, just like something about neural computation makes this impossible. I don't think that's the case.
Oh.
Right. I think in particular, you could do this thing where it's like, oh, if this bit lights up, it stops. I do think that that's possible. Right.
Well, so
and
people try. I mean, and I agree with you. Like, it is possible. And so there are attempts at this, like the differentiable neural computers, right? Or some configurations of neural Turing machines. It seems like the universe is conspiring against us, because the funny thing that happens is when you generalize those neural networks and try to train them in this way, it just becomes so much more difficult to train them.
Maybe we should discuss the so what question. So the thing that PETA's been driving at is, this algorithmic alignment of neural networks. And the hypothesis is there are certain fundamental forms of reasoning where you do require this kind of, quantification over potentially infinite sets. Just computing the nth digit of pi, or just sorting, like a set of numbers to arbitrary length. Now, the incredible discovery of neural networks is so many things in the world you can essentially interpolate within distribution, and it just works. Now, I'm a big believer in this system 2 idea that, there's a lot of gnarly perception type stuff, and then there's the system 2 where we do need to do this kind of symbolic reasoning. Is there a space where we need to have Turing computation for AI?
Even if you could solve all interesting problems, to humanity with a big enough Turing machine, like you construct one the size of the sun, and it's made out of neutronium and like whatever else, and like it can finally do everything we want. You can do it with a lot less energy, a lot less matter, if you can use programs that can utilize some unbounded, input sensitive amount of memory. So I think like that's, again, like it's about this program search thing, which is the best solution in the sense of like ones that are practical, energy efficient, whatever. Many problems, the best solution lies in this broader space of kind of Turing complete problems. It's certainly been the case for human programming. Like when, people could just write programs that were FSAs. Like we could have done that. We never needed to develop von Neumann machines and kind of like what's sitting on your desk, but we did because they were extremely, useful for solving real problems. And I agree with Paul that there's no theoretical limitation why you can't train a neural network, to search the space of Turing programs. It's just we haven't figured out how to do that yet. And there's some tricks that we're missing. And I'm just saying all the current architectures do not search that space. They search a small subspace, and there are many interesting problems outside of that space.
Yeah. Can I frame it a slightly different way, which is there are two directions here. One direction is what Francois Cholet says, and you've just been alluding to, Keith, which is that we build a kind of AI which is almost purely a discrete program search. And the other school of thought is we do some kind of neurosymbolic combination. And Josh Tannenbaum has been doing a lot of interesting work here with, Bayesian program search and Dreamcoder and so on. And even things like fun search and Q star and tree of thought and stuff like that is a step in this direction, which is to say we start with this interpolative continuous vector space, which has been trained on a whole bunch of stuff. And then it's still traversable in that space. So if we do some kind of search controller on the top, of course, it's not going to be searching the space of Turing machines, but it will give us a margin on the top, which will find all sorts of interesting things. So just doing this Q star algorithm where we're in an LLM and we search a whole bunch of trajectories and we have some kind of cost function or whatever, and that margin might give us a dramatic improvement. But I still think that there's a whole space that we're missing that is not traversable through neural networks. Let me just say as well that what's happening right now is the real intelligence of these GPT models is the collective search process. It's the collective intelligence. So we're all using it, and we are just putting different inputs into it. So we're a bit like tree of thought. We're a bit like Q star. All of these people all over the world are just finding these interesting prompts, and they're kind of traversing the input space and they form like a layer of intelligence on top of the LLMs. And I guess the question we're asking is, maybe the first step would be just to replace that human search process with something automatic.
Well, I mean, I'm just going to jump in real quick and then let Paul go, which is two things. Again, in my mind, there's no theoretical reason why. So again, a Turing machine is a finite state automata with a read-write memory. There's no reason that finite state automata can't be a neural network. It's just that we haven't yet figured out how to train neural networks that function in that way, at least not for general purpose, efficiently, et cetera. And I think as to whether or not, like, which direction is ultimately going to be the more successful pragmatically, I don't know. It's a big mystery to me, but it seems like, the efforts of, Paul and, and George's company is working towards that route, which is like, give us a domain specific language that's like, in a sense, many generations higher than Dreamcoder. It's like a domain specific language that lets people program these complicated modules and machine learning more effectively, and I see no reason why that wouldn't also empower automated programming as well.
Yeah, broadly, I like that story. Yeah, I think I've been confused when this question has come up, because I thought it was the claim that like we somehow can't do this. And I don't know, like, I might be wrong again, but I don't, at my current level of understanding, see any like fundamental obstruction to developing neural networks that are, Turing complete, or whatever the magical words are for it, right? I don't actually see any like essential obstruction. We may not have figured out how to do it yet, but I don't see why that's impossible.
Well, they have to be a neural network with a read-write memory. Yeah. And once they have that, so they're augmented, neural networks. And then once we figure out how to train them, like, kind of open season on every computable problem.
Yeah. I mean, I think we can agree that it's probably possible in principle and currently not in practice, and it is a very, very difficult problem. I mean, we can all agree on that.
Yeah. Well, it's definitely currently not nobody's doing it, that I know of currently. I think it is really difficult. I think there's some magic tricks that we haven't found yet, and they may lie in this direction of, starting to apply category theory to design domain specific languages that have the semantics that we need.
Yeah, I mean, another thing was when I first read your paper, I assumed that there was some kind of, I guess I visualized it as a kind of compiler. So now it's a bit like, imagine we had something like JAX, and we did to JAX what TypeScript did to JavaScript. So, we add typing to it, we add compositional semantics and so on. And what we've done is we've now created this whole like interface basically to understand how to build the next generation of neural networks. And then the system is a bit like a compiler. So it will compile down to neural network modules that have, GDL constraints or algorithmic constraints and so on. And in the future, maybe even symbolic networks that it would just auto-magically do all of this stuff. Because what we want to get to is we need to get away from the alchemy, right? We need this compiler to kind of do the hard work for us, so that, just all of these problems that we're seeing at the moment just are a thing of the past.
I have just a quick question, because is one proper way to think about this that we are pushing a lot of the work, we're pushing a lot of the necessary semantic work to syntax, where it can then be automated. Like, that seems to be really like the story of mathematics too as a whole. It's like creating new syntaxes and new sets of rules, new domain specific languages that effectively systematize and allow to be automated, the necessary reasoning.
Yeah, I think that the way that the mathematician might phrase this, and I think this is what Andrew actually provided a very nice description of, is, the history of mathematics has taught us that abstracting a lot of the specificity away and making your problem statement more and more general, well, you might think, would make it harder actually makes it easier, right? Because the point is, if there's a lot going on, I don't know what to grab onto. But if I reduce the things that I'm allowed to grab onto, I can think more clearly about them. And the elegance allows me to reason carefully about them. And here I do mean reason, right? In the sense of coming up with reasons for things, right? Why does this do this? How does this work? Those kinds of things, right? So you abstract away the sort of like essentially analytic detail to to a problem, and then suddenly it becomes tractable, it becomes conceivable. I would say that what really category theory does is it abstracts the idea of a semantics, right? That's really what it is, right? Is because you say, oh, what is a category? It is a universe of some particular kind of thing. You know, your objects are the instances of that kind of thing, and then your morphisms are the computations that go from one instance of that kind of thing to another instance of that kind of thing, right? So it is really a theory of abstract semantics.
Just a quick question on that. Like, aren't you allowed to have more than one type of object in a category, or no, or does that have a different name?
Well, so so what do you mean? What does one mean?
I mean, can I have a morphism that transfers an object of type T to an object of type S, and then a different morphism that
but they are
transforms it
all
back to
objects of the same category, right? Different types
same category, but different types.
Exactly. So the point is, like, the notions of object and type are not they're not exactly the same thing. Right. For example, if you're thinking in terms of Haskell, which is like the most likely way that someone like listening to this or watching this, like this is going to be the most familiar thing, is there's this category Hask, whose objects are all of the possible types that can be formed with Haskell, and whose morphisms are all of the possible well-typed functions.
Okay. Right. So is there a particular name for a category with objects of more than one type?
Well,
like
it's
multi-type category or something.
I mean, I think it's the kind of thing that once you stare at it long enough, the question ceases to make sense. I think it's that kind of thing, right? Whereas it's sort of like, it's trying to like mix these metaphors a little bit too rigidly that introduces that. I would specifically say is like any given category is like the universe of a particular kind of thing. Right. And then if you want to talk about categories where you've got multiple different kinds of things, those you're actually talking about working in the category of categories and talking about functors and, natural transformations between functors, right? You're talking about relations between the universe of things of this kind and the universe of things of this kind, and, translations from the universe of things of this kind into things of this kind. So I'd say for any given category, you've got one kind of thing. But the point is, that doesn't mean that category theory at any given time is only about one kind of thing. It's actually about structural relationships between the universes of different kinds of things all at once.
I'm going to have to go back to those tutorials. Oh, by the way, there are these online tutorials done by Brendan Fong and some others. Those were the ones I was trying to go through. And,
no, those are great.
And it's fun because it's really enjoyable when you come across a topic that blows your mind, and the way like I kind of quantify a mind-blowing thing is if I understand it the day that I learn it, and then somehow the next day totally no longer understand it. It's kind of like it's kind of mind-blowing. So here's just kind of a funny question for you, and answer this any way you want. But which do you think is more mind-blowing math? Category theory or number theory?
Oh, category theory. The thing is, number theory, I don't understand it well enough to have my mind blown, right? I don't know what the weird results of it, this better. I don't know what the weird results coming from number theory mean. I have no way to interpret them. It's like, what? There's a number that does that, right? This particular number field is like, has some weird, abstract property relative to another one. I don't even know what those things mean, right? Because I'm not a number theorist. I haven't spent forever thinking about this, but I have at this point spent, like at least 10 years thinking about categories, and so I've found it to be a lot more mind blowing, because to have your mind blown, you have to understand what it means, right? And I do feel like, at least whether it is my own sensibility or essential to the discipline, I won't say. But I kind of think that category theory is more mind-blowing. Otherwise, I'd be a number theorist. But You know,
No, I like that. In order to have your mind blown, you have to first understand so it can be blown away.
yeah, because otherwise it's just complete mystery. And it's like, mystery is not interesting, right? Mystery that has the flavor of, I can understand this. That's interesting. Otherwise it's just like, huh, that's weird. And I move on with my day.
Got it.
Right. It's got to trigger the senses like, oh, this something weird happened and I can make sense of it. I can make sense of it. I haven't made sense of it, but I can. Right. I have to have that taste. Otherwise it's boring.
That makes sense.
So one other thing that confused me a little bit about the category paper is you were talking about being able to, for example, create an analytical pathway, if you like, between, let's say, a list or a tree. And I'm understanding the work as being about data rather than algorithms. And I think the way I understood it was, again, I was kind of brought up on Petter's work with algorithmic alignment. So he's thinking about getting neural networks to behave as if they are doing sorting or doing like Dijkstra or something like that. And I was thinking about, this could become a kind of system 2 toolkit where I need to have these algorithmic primitives and I can compose them together. So do I understand correctly at the moment that it's almost about types of data rather than types of algorithm?
I don't know if those are actually that different. Right, and the reason why is if I have a well-typed function from one data type to another one, that's both about algorithm and data, right? That talks about what you're allowed to do with data is exactly what the algorithm does, right? So the point is that I don't think that distinction is meaningful.
Interesting.
Yeah, kind of. I mean, I think I sort of... I have a lot of sympathy to that point of view because this goes back to when I first learned about algebraic data type theory and its application to programming languages. I started to really realize, data and I don't know what the right word is, but data and type, data and set of transformations allowed on that data are almost intertwined into the like one isn't really useful without the other. It's kind of a weird duality or something. I'm not sure how to phrase it.
Yeah, no, I mean, like I might, hazard at some sort of like, dialectical fixed point. It's like one informs the other, and like the notion of type and well-typed function reinforce and define each other, right? It's a very much a functionalist kind of thing, right? Type theory is the core of like, a syntactic treatment of a synthetic mathematics, right? Or at least that's, the weird, not fuzzy, but like rarefied and unbelievably abstract world that, through which I discovered type systems. Right. But
maybe another way to think about this, maybe this is related to, get your opinion on this, Paul, that may help Tim for us to think about is, for many, let's suppose you have, and I'm just going to say class. I'm not trying to be like object oriented or something, but suppose you have a type, that's interesting, like whatever, complex numbers. You're doing a lot of programming, and complex numbers are useful. Yet there are many representations of that complex number. You could like literally store it as a piece of like literal data that was an angle and a magnitude or two, XY coordinates or whatever. There's many possible data representations of it, and it's just irrelevant. It's like you choose one based on like, whatever works, whatever's efficient, whatever I feel like, whereas all the important and interesting stuff is at a higher level than that.
I would hazard that I would be uncomfortable with the statement that it's irrelevant, right? And in fact, so here's one of the maybe this is not what happens if you're like in graduate school for mathematics in places where category theory doesn't have this sort of like, somewhat deprecated history, using deprecated in this kind of like a slang way. It's like, oh, this is kind of like not approved kind of mathematics, right? North American math, like specifically American Math
heretical.
Academy. Yeah, exactly. It's heretical, or like people don't like it so much. Like, why? It's like, well, because it doesn't feel like you're doing anything, right? Why do you do mathematics? What is the pleasure? It's like, I want to feel like I'm doing the computations. And category theory has this nasty habit of telling you that you didn't do anything, right? But
it's like that scene in Good Will Hunting where, you know, they're up there. There's some circles and lines drawn on the board, and he goes up and erases one and draws a line somewhere else, and they're like, oh, you know, it's like, you know, well, what?
Yeah, I mean, the thing that is sort of that about category theory is actually, you know, Grothendieck had this statement that was like, if it's not obvious, you're not ready to work on the problem yet. So, and, you know, he had this whole, you know, principle of like theory building for problem solving. And one of the aspects of theory building for problem solving is you develop a vast library of equivalent or at least related representations of similar or the same concept. And you solve a problem by finding the one in which it's obvious. Right? It's sort of, it's a shamanic mathematics. It's a mathematics about understanding something and then not really having to do that much, right? The point is, think about this in the right way and it becomes trivial. This is or not trivial, or at least like clear, right? You know, this is very much right.
So
The task
I
of
see
science
the
is to
point
carve
there.
nature at the joints, right? Like that's the thing. It's like, well, then you have a bunch of different ways you could carve this up. Find the one in which it's easy. Right.
No,
And
okay, so that makes sense. I mean, like thinking about all the different possible representations of complex numbers as a data representation is still, again, informative of the algebra that you're, you know,
yeah,
trying
exactly.
to use
Which
on them.
what
So
are you
they're
going to
just
do with it?
inextricably linked.
Yeah, like what are
Yeah.
you going to do with it? That determines which representation you should use.
Yep. Yep.
So you're telling me the scheme people were right all along that code is data? It's just
Oh, absolutely. No, they were completely right. Yeah. No, our what was it? 10th grade learning scheme. Yeah. That definitely informed my sensibilities a lot more than I realized, you know, because I went away from doing like math and science for quite a while before coming back to it as an undergrad. And as I've gotten deeper into mathematics, I was like, oh, I really did drink this like functional programming Kool-Aid of this like deeply pure 1970s variety a long time ago. And whether I understood that that's what I had done, I absolutely had. But I do think that they were right. Like the difference between data and code is like there isn't one. Right? Actually, like the difference between data and code pops up in neural networks a lot, right? You know, people like thinking like data is like, you know, training data is like, what is like, training data is the goddamn program. The neural network is the compiler, right? You are compiling training data into the final state, which is going to be the function that you're actually going to use, right? This is why I think eventually all of the copyright lawsuits against the major AI companies will go through, because they are using copyrighted data to program their machines. That's exactly what they're doing. It's not learning is bullshit. It's programming, right? It's a weird programming that works by way of like differential, like sort of, you know, like a slightly mutant differential geometry, but it is just programming, right? You are literally programming your models with data, right? So any distinction between data and code is nonsense.
That is very interesting.
some great sound bites from this conversation, Tim. For me, it was kind of a compound of little different, you know, things that I was taught. Like when I learned that you could exponentiate matrices.
Yes.
You know, I was like, wow, this is weird.
Yeah.
You know, when
Thank God for power series.
Yeah. Oh yeah. Well, that's another cool thing about power series is when you finally learn why, you know, e to the I pi equals -1. You know, and you look at the power, like that's kind of mind blowing. And then when I saw how to construct, I think it was piano arithmetic from this kind of algebraic type theory, you know, perspective and things like that, it just all adds up to the same really fascinating, you know, I don't know, fact about the universe or fact about logic or something.
Yeah.
So we've been using some terminology like syntax and semantics. Can we just like zoom out a little bit? What do those terms mean, and how are you using those terms in this context?
Okay, so what I mean to say is, okay, syntax, formal expressions that you do not assume have any meaning, but instead you just have rules that allow you to combine that thing. So purely formal constructions, usually in terms of symbols, whether it's graphical or text, that's sort of irrelevant. But the point is it's purely formal manipulations of symbols, right? And semantics is when those are interpreted as meaningful, right? And the kind of two-category theory that I've been talking about is like an abstract semantics. Right. Whereas this category with like a single object and these endomorphisms, this like classifying groupoid of a group thing, that is the sort of like, that's the categorical avatar in this case of like the syntax of being able to write g.x and g'.g.x, that kind of thing.
Okay. So, from a linguistics point of view, like people understand semantics to me to be the meaning, the aboutness of a word. So, for example, I could say wagger and dog, and it would point to the same cognitive category, which is a dog. But in this framework, just help me understand exactly like what is the semantics?
That is a good question, right? Because you're asking about semantics in this very particular way, as like, what is this thing about? And well, the syntax allows you to write down constructions or operations which are manifest in the semantic category, right? So the category is the world in which that syntax is interpreted as, be it things like elements, or be it things like functions, or be it things like transformations.
Yes.
Right.
Yeah.
So the category that there's this semantic category, and then the fact that they're also encoding like syntax as a category itself, that ends up, opening up another sort of can of conceptual worm, sort of breaking down like the easy distinction between syntax and semantics. But the point is, the story that they were telling, and this is sort of instructive, and this is sort of very much what Andrew says, is, okay, so you start with syntax, you can write that down into the universal category that has that syntax interpreted as morphisms. And then you look at functorial semantics of that. So that's the interpretation of this universal category in which those terms have meaning, right? Which means they have no other meaning other than the formal relationships between them that you specified in your syntax. And then you take a functor out of that thing into something else, and that interprets them. So that's this notion of functorial semantics. The story that I'm talking about is, I'm not even worried about ever writing down any individual terms. I'm just interested in sort of this two-dimensional graphical picture that allows you to talk about what kind of thing algebra is at all, right? So for the story that I was interested in, this, and like the way I come to this is, we don't even really ever study the elements. Like, I want to get away from that, right? Because the elementary perspective, while it's useful and helpful for like the analytic construction of these neural networks, it's not that good for proving properties of those networks, right? It's pretty easy to, like, you write an expression that has 5 to 10 terms, suddenly it's very confusing. Whereas you draw an element like a diagram that has just like 5 or 6, 1 or 2 dimensional pieces, and you can derive formal properties about it. It's a little bit easier.
Okay. I mean, because we were saying earlier that we could use the example of group theory, and I could look at all of the like symmetry preserving transformations of a triangle, and the aboutness, the semantics is the triangle.
Yeah, the transformation, exactly. It's about the triangle, it's about the actual transformations of the triangle. Yes. And then the syntax is just these things as elements of the abstract symmetry group.
That makes sense. So when I was discussing this with Andrew, he said that the reason this separation is useful is because if you think about it, it's like you're talking about two worlds, and he was arguing that we have less representational ambiguity in the world of semantics.
Yes.
So there's a kind of asymmetry. So for example, using this group analogy of the triangle, we have these high precision. We can actually draw a grid of all of the symmetry preserving transformations, and now we've got a very high resolution way of understanding that triangle. But I guess the question is, though, is it really true to say that there is less representational ambiguity in the semantics? I guess like the question I'm asking here is, are these semantics ordained by God, or are they purely a human construct? I mean, does semantics just mean something to humans?
I wouldn't say that they are ordained by God, but I would say that what you can do is, like, you can have like the initial semantics of something, which is right. So if a category is some like abstract universe in which things like a universe of a kind of thing, and then morphisms between that kind of thing, right? You can talk about like the initial semantics of something, right? And this means the one that like the semantics that has only the properties that are necessitated by the syntax and no other, right? And that is genuinely, necessarily less ambiguous than any particular syntactic presentation of something, right? So I'm not going to be able to come up with two distinct presentations of a group, but the point is I can write down things like groups by way of generators and relations, right? But there may be, and usually are, many different ways I could write down the same algebraic structure with different syntaxes. However, there is only one semantics for that thing.
Cool. Now, so you've written this paper, right? If you were to give me a 1-minute elevator pitch of the paper, what would it be?
Title of the paper is Categorical Deep Learning, an Algebraic Theory of Architectures. One thing that like the hardcore category theorist amongst us might take objection to is that the words algebraic theory actually have a formal meaning in category theory, and that's not actually exactly what we mean, right? An algebraic theory to a category theorist is like a Levier theory. It's one of these syntactic categories of like the allowed manipulations and stuff like that. Whereas what we mean is specifically architecture as being the semantics of this sort of these universal algebraic notions. So that's the title of the paper. Gotten distracted by this statement that we said algebraic theories. Maybe that's not the best name, but it's a pretty good name. Why is it a good name? Because the point is that we want to say that all of the things that have been studied in GDL and significantly more examples, all of them are in fact instances of algebraic structures, be they structure-preserving maps, i.e. morphisms between algebras for monads, or structure maps of algebras for monads, or the appropriate dual constructions. Say these are sort of these like universal structures, and then we're interpreting them into a two-category whose objects are vector spaces, whose morphisms are parametric maps, right? A good example of the kind of parametric map that pops up in deep learning is a ReLU network is a parametric function, right? Because for any given choice of weights in all of your various layers, right, you get one function, but you don't really want to think about those functions as distinct. You want to sort of group them all together. And so this is why there's the innovation of this notion of the parametric function. And then you want to talk about being able to change those parameters. So that requires the introduction of this notion of reparameterization. Yeah. Right. So specifically what we develop, or we don't develop it in this paper, right? This para has been around for some time. But what we really do is we say, hey, if we do two-dimensional universal algebra valued in these categories of objects, parametric maps, and reparameterizations, that allows us to talk at a very high level of abstraction about the kinds of things like the geometric priors of GDL, or the structure maps, which are exactly the representations of groups that are like the foundation for GDL. It allows you to talk about it in a far more abstract way that more naturally generalizes to algorithmic constraints, as opposed to merely sort of conservation law type constraints, which is that which groups are really good for.
Okay, so let's just talk broadly about abstraction, right? So what is the purpose of abstraction? And in this particular case, give us an example of a powerful abstraction that would, change the way that we reason about neural networks.
Okay, what is the purpose of abstraction from a mathematician's standpoint, if you want to be utilitarian about it? The purpose is, do I want to climb a mountain with a lot of incredibly specific gear? Or do I want to learn to be a mountain goat? Right? That's really what the purpose of abstraction is. The purpose of abstraction is getting away from all of these specifically adapted tools and say, okay, these are the tools that I'm going to allow myself to use for it. Suddenly the problem is more general, and like you might think that that's going to make it harder, but it doesn't. It just teaches you, no, don't hold on to the like individual unique specificities of each instance. Those are distractions. Those are not the structural properties. Right, those are the specifics of specific instances. You want to get away from those because those are distractions from how you solve the problem in a way that's actually comprehensible.
Okay. I mean, I think that there's an element of there's a sea of complexity that we need to tackle, but the mountain goat's quite an interesting example because I would say that's actually an example of specificity rather than generalization. But then we get to canalization.
Yeah, so that's fair, right? This is a question of mixed metaphors, right? And getting excited about one and getting stuck in it, right? So this is a train of thought that gets a little bit too far down in one direction. But what's the point? The point of abstraction is to get away from all of this extra baggage that you might think is providing you information but isn't. right? You might think that like the easiest way to solve a problem about the natural numbers or about the integers would be to like know a lot about how 2 works or how 3 works. Turns out it's way easier to develop the abstract notion of a ring and develop this like massive library of theorems about rings, right? And it's actually by abstracting away any of the details that forces you to think in a principled way.
Yeah, so I get all of that, and duality, for example, is a wonderful feature of category theory, because you can prove something in one domain, and because you have all these categories set up, you have the morphisms and so on, then that propagates. And I guess this was something that we used to do manually in scientific theories. We would have to kind of prove duality on a case-by-case basis.
Yeah, so this is a sense where like category theory allows you to do it once and then interpret it into various contexts and see it as an instance of the same thing.
Right. But coming back to the mountain goat example then, so because that's a weird juxtaposition.
It is.
Because it's both specificity and generalization. The reason I said canalization is because we know how evolution works, and how living things work. There's this canalization. So like this goat, it might seem like it's the perfectly well adapted and specified physical form to work in this situation. But actually, if you so we're talking about compositionality. If you decompose it into its component parts, those parts are they represent the ultimate form of generality.
Yeah, I would buy that.
Okay, but then one thing I think about here is just how fundamental, how universal these general components are, because we want to build a structured picture of the world out of building blocks which appear universal, and probably they're not. Maybe some of them are universal, maybe some of them are not universal, but we want to have the Lego set for the universe.
No, we definitely want to have the Lego set for the universe. I don't know what the Lego set for the universe is, and I doubt that there's only one. But what the last, 60, maybe 80 years of mathematics have told us now is that category theory is a damn good one, right? It's a principled theory of abstraction, right? It says, okay, what is a good abstraction for a notion of structure, and what are the principles by which you should reason about it, right? And it becomes this task of, hey, the category theorist sees a problem in some particular domain and says, what are the tools that I know that kind of map onto this? How can it tells you which parts of that might actually matter and which parts of it might not, right? So you develop a categorical abstraction about it, and then suddenly it becomes often easier to think about, and it becomes easier to prove things about.
Yes, and I think that the miracle of human cognition in particular, as we were alluding to with Keith earlier, is this. I think abduction is the same as categorization. So I think we select these categories, we create that. Maybe we select them, maybe we create them. I mean, that's an interesting philosophical thing, but we have the ability to do that, and we're carving up the world, and it's our way of overcoming the sea of complexity in the universe.
I would buy that. That's a good story. Is it's sort of like what happens in neural networks is like, do you want trillions and trillions of parameters that allow you to recreate exactly this, or do you want a much lower dimensional space of explanations from which you can rederive and constantly be checking against what you're experiencing?
Yes, and this is the story of parsimony in general. So on the one hand, you could have an inscrutable large language model, which is just a sea of neurons. On the other hand, maybe there is some kind of decomposition of language model, or maybe just forget the language model. Maybe there is a decomposition of reality, and no one knows how complex that thing will be, right? Maybe it's possible to really decompose it down into like 1,000 types or something like that. But that must be a better way to go than to have the inscrutable language model.
I definitely think so, and that's definitely the bet we're playing with Symbolica.
Okay, now there's the question of what we mean by reasoning as well. So I think we intuitively agree, I think, that in order to reason, we have to be working on this kind of decomposed, parsimonious view of the universe. And there's a relationship between reasoning and generalization. So type 2 generalization, as we understand how I reason about chess, for example, is we have this discrete categorical model of the chessboard, and reasoning is kind of like taking trajectories and doing various forms of deduction and inference and so on in that discrete set. So that's reasoning. Is reasoning more complicated than that? I mean, maybe like, what do you think reasoning is?
My definition for what reasoning is heavily informed by what I know from the work of Sperber and Mercier, right? I am really influenced by the idea that what reasoning is the coming up with reasons for things. Reasoning is about explanations. Right. So this is one of the reasons why I sort of bristle against the sort of common ML use of reasoning, right? Is I'm not entirely comfortable with the term because I think it's a category mistake, right? I think reasoning is coming up with explanations for things, right? Deduction is really what we're talking about, or induction, right? Things like that. That's mostly what we're talking about. So we say inductive reasoning and deductive reasoning, and I know that that's sort of popular language, but I've sort of fixated on this perhaps idiosyncratic use of the word reasoning that has sort of informed how I think about a lot of the stuff in the last couple of years.
Interesting. Yes. So there is a school of thought, as you say, that reasoning is deduction, induction, and abduction.
Yeah.
Neural networks definitely do not do deduction. I mean, if they do it, it's only because they've memorized instances of it. They possibly do a form of induction, and they definitely do not do any abduction, which is, like generating reasonable explanations for things. Or if they do it's only because they've memorized human instances of it. Does it matter if because this is kind of like, what Bostrom says about intelligence and goals are orthogonal. And what he's saying is that goals are universal, and this is a really common thing in symbolic AI. And people think that intentionality means that we have goals, and these goals are fixed. So the reason you behave the way you are is because you had a goal, and that goal is like a universal thing. It was always there, and that guides your behavior. Another school of thought is that intentionality is as if, which means like you have agency if you could construct an explanation that explained your behavior about yourself or other people. But is that a good explanation if it's just a model rather than being what you actually did?
It's a really good explanation if you can make that thing formal, right? If you can say, okay, here is my sort of purely syntactic description, say, of what that reasoning is. And then I can have a formal interpretation of that and say, actually, this did work like that, right? It's certainly not going to be the only explanation. But the point is, it is a good one, right? So that's the kind of thing that I find most interesting.
And what makes a good explanation? Is it just predictability, or is it intelligibility, or is it something else?
I think intelligibility is hugely important. An inscrutable reason is like having no reason at all.
Exactly. So we intuitively agree that the reason why language models are, it's not so much that because there is obviously a reason why they do things, but we don't understand what the reason is.
Right.
And we intuit that the reasoning is not robust because first of all, if you just look at the activation pattern of a neural network, it's like you perturb the input by a tiny amount, and it's almost like it activates completely differently. So we think that the reason it does stuff is super, super brittle, whereas we think that the reason we do things is robust. And maybe we're just being human chauvinists or whatever, but we kind of think that kind of reasoning has an elevated status.
Yeah, I mean, I think it does, but I don't think it's elevated in the sense that neural networks can't do it. I think it's that existing architectures don't.
So what would we need to do to a neural network to make it more robust in that way?
This is in some sense what the paper is about, right? So the paper is about how you might talk about algebraically structured neural networks.
So is this almost like when we deliberately canalize a neural network, we are, I mean, obviously this is all on a spectrum, but by reducing this kind of chaotic, random trajectories, random activations and so on, by creating a robust activation pattern, which is perhaps more, if not completely intelligible, then it's going towards reasoning.
Yeah, I think so.
Yeah. So we should do some category theory 101, because I'm sure that the audience know nothing about category theory on average. So in your paper, you actually had a really beautiful introduction or a primer to category theory where we kind of like go through the concepts one by one. Can we do some of that now?
Yeah, I'm glad you think so. So one story of where you get to categories is the one that Petter will have told you, 20 minutes ago in this video. Right, and he talks about it as, okay, so you start with groups, and then first thing you do is that you relax the requirement that all transformations are invertible, that they can be undone. And then the next thing that you do is you relax the criterion that all transformations can be composed. And that does indeed get you to a notion of category, right? Because a category, at least a small one, is a set of objects together with a set of morphisms that have a composability criterion on them, which is that the end of one arrow has to be the beginning of the next one, and they have a composition law that is associative, meaning if I've got three of them, if I compose the first two and then the third, or if I compose the first one and then the composition of the second and the third, I get exactly the same thing.
Okay, so there's this associativity axiom, and there's also an identity axiom, right?
Yes. There is always an identity or endomorphism of every object.
Okay. So let's just be clear here. So a category, it's like a set of objects and morphisms.
Yeah, it is a set of objects, and then it is a parameterized family of sets of morphisms, and is parameterized by pairs of objects, one being the source, the other one being the target, or in different language, the domain and the codomain.
Okay, so I mean, let's just sketch out an example. So that in the context of like GDL, what would that be?
Oh, okay, let's go do something easier. Let's look at the category of sets. Right. So I've got my objects are sets. My morphisms are functions of sets. Not all functions of sets are composable because I can't apply a function that takes in input from a set of three things to a set that has two things, right? So that's where the composability criterion comes in.
Okay. So let's talk about morphisms. How do they work?
So they're just this is the magic of category theory, is like the sense of how they work is, well, they compose in an associative way and there's nothing else to them. You've abstracted away any of the specificity of those things being a computation or doing something. They're simply there, right? And you're reasoning about, or here I'm using reasoning again, but the point is you're thinking and like doing inference, reasoning, fine, I'll just say reasoning. You're reasoning about how you can compose them and what properties, those compositions have.
Okay, so in the GDL show,
yeah,
there were these groups, and there could be the group of triangles, but we're also talking about things like SO3 or things like ones that preserve rotations and angles, or there is ones that preserve like translational equivariance and so on. So and these groups needed to have like four axioms that they conformed to.
Yeah, right. So groups are sets together with a binary operation and a specified element, such that, that specified element, the unit of the group operation, acts as the identity transformation if you put it in the first argument or in the second argument, and that multiplication is associative.
Okay, so these morphisms, it's a kind of similar concept, right? So it's a transformation between two things, but there has to be some kind of structure preserving characteristic.
Well, this is the funny thing, is what you're doing is you're abstracting away the structure that it preserves and simply talking about what kinds of things can you do with structure preserving maps. It's like, I don't know, but I can compose them. And so the idea is, hey, let's just talk about what we can know about mathematics just in terms of the notion of composable morphisms, of composable functions. We don't look inside the functions anymore. We specifically abdicate that position. We say, okay, I'm going to reason about how I can compose stuff and nothing else and see how far I can get. And what's absolutely demented is how far you can get with just that. Right? You might think that, no, I really need to see what's inside these things. It's like, for a lot of properties of mathematical structures, you don't, right? Is if you abstract that away, suddenly the same claims can be made and proved in various different contexts.
So, so just to really spell it out, when you say you can compose these morphisms together, because you were talking a little bit before about it almost being an interface, a bit well, but Lego's a good example, so there's a square peg, there's a square hole, these two things go together. So for them to be composable, it just means that if there's a compatibility between them, you can kind of, plug them together in any configuration you want.
Or not any configuration, right? There's usually only
compatible. Yeah.
Exactly. There's like the ways that you are allowed to, right? So suppose I have one function f, it goes from a set x to a set y, and I've got another function g, that goes from y to z. Right? I'm allowed to compose first f then g. I'm not allowed to compose first g then f.
Mm-hmm. Okay, so we've done the basic category thing. Let's go to the next level of abstraction. Let's talk about things like functors and endofunctors.
Okay, so what is a functor, right? So first, we've said a category is, a class or a collection or whatever. Usually it's a set of objects together with this doubly parameterized family of morphisms that you can compose. Well, that's a mathematical structure in and of itself. So I can ask, what are the structure-preserving maps between categories? These are the things that are called functors. What does a functor do? A functor comprises an assignment of the objects of the first category to the objects of the second category, and the morphisms of the first category to the morphisms of category in a way that preserves composition.
Okay, so again, let's bring this to life, because we were talking earlier with Keith about you could, for example, transform a list into a tree or something like that. So it seems like the objects are very different, but you're still transforming between them in a way that maintains these properties.
Yeah, so lists and trees. So let's talk about, lists valued in a particular set, right? So what do I mean by lists valued in a particular set? I can think about the monoid of lists valued in a set X. I can also talk about binary trees valued in a set X, right? And it's still a set function between them, but it might preserve some portion of the monoid structure of lists and of the algebra for a monad structure of trees.
Mm-hmm. So let's move up one level of abstraction. So let's go to two categories. How does that work?
Okay. So we've talked about categories, and now we've introduced this notion of functor as structure-preserving maps between categories. Natural transformations suddenly pop up. What the hell are they? Mm-hmm. Well, first off, they're essentially the reason why category theory is invented. Right. This is sort of like, I think if you ask McLean and the other guy whose name for some reason I can't remember, Eilenberg, excuse me. If you ask Sammy Eilenberg and Saunders McLean, like, why did you invent category theory? The answer is, well, we needed enough to explain what natural transformations were. Right. And so what happens? So suppose I have two functors. I've got some category C over here and I've got some category D over here. What a natural transformation is a compatible family of deformations. It's a deformation from one functor into another one, right? So if I've got C over here and D over here, right, and I've got one functor F and I've got another functor D. A natural transformation is a two-dimensional morphism that goes from one functor to the other one. Data-wise, what does it comprise? It is, for every object of the source category, it is a morphism in the target category that goes from the image of that object under the first functor to the image of the object under the second functor. And it satisfies this criterion called naturality, which is that this deformation is compatible with the morphisms of C interpreted by the functor F and the functor G, right? So there's things called naturality squares. If there's sort of, say, suppose I had some function F from A to B in the category C, and I had two functors, capital F and capital G, right? The natural transformation has components, which are going to be maps of the form F of A to G of A. And those are supposed to be compatible in the sense that a particular square commutes. And what is that square? Well, you have F of F goes from F of A to F of B. You have G of F goes from G of A to G of B. Mm-hmm. And then you've got these two vertical things. This one is the component of this natural transformation at the object A. This one is the component of the component of the natural transformation at this object B. And the criterion is that this diagram commutes. What does that mean? That means that if I compose this thing and this thing, that is equal as morphisms to the composition of this one and this one.
Let's talk about monads. So what are monads?
Okay, so what monads are is a gorgeous abstraction for things like group actions. Or excuse me, not for things like group actions, but for the notion of group action, right? So monads are things that have algebras. Let's look at a group action for a moment. So suppose I wanted a group action on an object X. Monads are hard. They're the kind of thing that, like, I used to find them really confusing, and now I still struggle to explain them. But it's the kind of thing that you're like, well, you've accepted this long enough. It's like, there's this notion? It's like, there is no figuring out. There is only getting over.
Yes. Yeah.
It's very much that kind of thing.
I mean, but part of the motivation here is Andrew in particular. His lens of analysis, as I understand it, is monads. That's his main view on this work.
I would actually say, so it was in writing the paper, Bruno and I came to the DeepMind team with, hey, let's talk more about monads.
Right.
They were thinking in terms of, let's talk about functorial semantics of syntactic categories, right? And we said, well, fortunately, if you've got a syntactic category and you're looking at all of the things which are models of that syntax, there is a monad whose algebras are exactly the same thing as models of that syntax. Right? And what the monad does is it purely semantically bundles up all of the operations. Right? Here's a good example of a monad. List blank. What does list blank do? It takes a set X to the set of all lists valued in X. What is the extra structure of this monad? Because what I've just described is just an endofunctor. I haven't described the extra structure of a monad. A monad has a unit and it also has a multiplication, right? What is the multiplication of this endofunctor? Well, what if I take list of X? So what are the elements of the set list of X? Those are lists of lists whose entries are elements of the set X. What's the multiplication? I can erase the inside parentheses. I can turn any list of lists into a list by forgetting the next nested parentheses. That's the multiplication of the list monad. What is the unit of the list monad? The unit allows you to interpret things of type X as things of type list X, right? How do I do that? I take the element X and I associate to it the list that just has X in it, right? And the laws of a monad are compatibility between these two notions, between the multiplication and the unit. What it means to be an algebra for a monad, right, is to have a structure map that goes from, the monad operating on your object down to your object. What this does is this interprets, like this formally right? So, the monad is this abstract, this purely semantic representation of this syntax, right? So I think about, like, if I've got some monad T, I think about what Tx is. That's all the terms that I'm allowed to write with X and all the syntax that defines the monad T. And then I want to interpret that back into X, because that's what it means to have, like, the structure, blah, 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 this is tautological. That's what it means to have the structure of an algebra for T, right? What does that mean in the case of, say, this list monad? Well, the algebras for the list monad are these things called monoids, where monoids just have a binary operation that has a unit. You don't have invertibility. How fuck does that make sense? Okay, let's consider an instance of a monoid with which we are all familiar. Natural numbers. Okay, so I can take a list of natural numbers and I can interpret it as a natural number. What's the right way to do that? Well, I add them, right? This is the structure map of the natural numbers as a monoid.
What if there isn't a natural way to, let's say, turn a list into a single number? For example, you could multiply them. Like, why add them?
That's just one of the structures. There are lots of different ways in which a particular set can be endowed with the extra structure of being an algebra for lists. There are lots of different monoids on the same set.
Oh, I see. So you would have one per operation or whatever.
Exactly.
Yeah.
That's the point, is each, like, abstract conception of operation gives rise to a different monad.
Yeah.
Whose algebras are all of the different structures that can be written in terms of that operation.
Okay.
But the magic of the theory of the monad is it gets you away from having to write those things down syntactically. And instead, you can just look at the two-dimensional semantics of this.
Yeah, it's almost like a kind of templating function.
It's a pattern language for algebra.
Yeah, it's exactly. And this brings me to Haskell, for example. So Haskell has a few monads built into it.
Yeah.
How does it work in Haskell?
Oh, okay. So these are some of my favorite monads, right? So I am not a Haskell expert, so hopefully none of the FP zealots in the audience will crucify me in the comments for getting this wrong. But so in Haskell, a lot of the time, what do? You start with an endofunctor F.
Yeah.
Right? And then you want to talk about the monad generated by F, right? The free monad on F. Well, how do you do this? It's like, well, you sort of like infinitely compose F with itself, right? Why does that give you a monad? It's like, well, because the, take omega, i.e. the size of the natural, like the infinity, which is the size of the natural numbers, do f omega times and then do it one more time, that's the same thing as just doing f omega times. So that means f to the omega composed with f to the omega is just f to the omega. Right, so that's the multiplication of a monad. So you can go from the structure of an endofunctor to the structure of a monad in this relatively elementary way by believing in infinities.
Yeah, yeah. So what else do we need to cover on category theory?
For the purposes of our paper, right, what do you really need to know? Right, that's the question you've asked. You need to know what a category is. You need to know what a functor is. You need to know what a natural transformation is. You need to know what an endofunctor is. An endofunctor, that's one of the easiest ones, right? An endofunctor is just a functor from one category back to itself. You need to know what a monad is. A monad is an endofunctor, but it's also more. It's an endofunctor together with some extra data. That extra data is a natural transformation from the composition of that endofunctor with itself down to just one copy of that endofunctor. And it's a natural transformation from the identity endofunctor into that endofunctor that satisfies some properties, right? And these are the axioms of a monad.
Okay. And why do we need endofunctors? I mean, it must seem like a naive question, but why do we need to have a way of transforming something back to itself?
This is what constructors of a type are. Right? So how do I build lists? I have a notion of what the empty list is, and I have a notion of how to append something to it.
Yeah.
So the endofunctor that begets lists, 1 plus blank, like the 1. So if I've got a map from 1 coproduct X down to X, well, what am I doing? I'm picking out a special element in the set X, and I'm picking out not an automorphism, an endomorphism of the set X. I'm picking out 0, and I'm picking out successor. So I said that was lists. It's really like making them like interpret the natural numbers.
Yeah.
Right. But it's that kind of thing. So the point is the endofunctors are interpretations of abstract terms. Like, so that's exactly why like monads are particularly nicely structured. Yeah. Notions of abstract terms where the algebras for monads interpret those terms into the original object.
And where can people at home learn about this in more detail?
I don't know, where the hell did I learn about monads? I think I learned about monads honestly, I learned about monads from watching people give a bunch of talks about monads and eventually believing in them. If you want to actually read something about it, I'm sure probably the best thing to do is go on YouTube and look up monad and find someone not from the FP world to tell you what a monad is. I'm sure like some of the, the Catsters videos will do a great job of telling you what that is. Likewise, I'm sure there's some of like the Fong and Spivak videos from their MIT course years ago that'll tell you what it is. I'm sure it's covered in 7 sketches, and it's definitely covered in all of the sort of pure math oriented texts about category theory, like, the classic, categories for the working mathematician, or Steve Audi's book, which I learned a lot of category theory from. I finally understood the innate lemma by reading that book a couple of times. So it's going to be in lots of places. Essentially, just pick one and fight with it long enough, and eventually you'll get it.
Yes. Now you mentioned Levier theory earlier. What's
that?
Okay.
Formally, a Levier theory is a small category which is complete under the formation of finite products. Okay, that's not a terribly useful description of it, right? To say that it's not a terribly useful description of it is completely wrong, but it's the kind of, there's like the description of things that's exactly right once you know what it is.
Yes.
But but it's not the right way to learn about it. So why do you want it to be closed under finite products? Well, because finite products are exactly what allow you to phrase functions that are going from tuples of things to other tuples of things, right? So say I want to encode the laws of a monoid. Mm-hmm. Well, there's a binary operation for a monoid. So to encode that, I need a map from x times x down to x, right? So what a Levier theory is, right? Say the Levier theory, I'm not going to do it specifically because I'm fucking up if I try and do this right now, but what a Levier theory is it is a category which encodes the compatibilities and relationships between a bunch of N to M array operations. Right, so it is a syntactic category that has no structure except specified relationships between a bunch of different N to M array operations.
Paul, it's an honor.
Yeah.
Thank you so much.
Yeah, that feels pretty good.